on direct epitaxial growth quantum dot lasers grown on silicon. I'm a physics major here at UCSB, and I worked under Justin Norman and Dr. John Bowers in the ECU department here. And so the reason we want to integrate photonics is because we're having a bottleneck within data centers between servers talking to each other. So we've had photonics integrated in large scale, so like the huge wires that are laid down and the wires running to houses and things like that. But we don't have integrated photonics within the data centers, and that's where we're really hitting the bottleneck with speeds. So in order to combat that, we want to integrate photonics into the data center so that servers can talk to each other faster, kind of like what Ian was talking about earlier. The problem with this is it's pretty expensive, and it's also very tricky to manufacture. It's very expensive methodology. So 3,5 materials like indium phosphide and gallium arsenide, they can't be grown into very large wafers, and they're also very expensive. So silicon would be preferable because you can grow much larger wafers and it's much cheaper to manufacture. The problem with silicon is that it has an indirect band gap. So it is not very good for lasing like when you just have it by itself. So you have to grow a template on top of it so that you can have a 3,5 material that is good at lasing and has a direct band gap. The issue that this causes is it causes dislocations because there's a crystalline mismatch between silicon and the template grown on top of it. And that creates these little things, which are just flaws between the interface. And dislocations are a problem because it creates an avenue for electrons to escape out of, which makes for a very inefficient device, which is not great when you're looking for these very small scale devices. You want as efficient as possible. So this is the structure of a laser. Here is a cross section of it. So you have your base silicon, you have your top template, and then you have your two cladding regions, which transports the electrons and creates the electron-hole disparity, which gives you the electrons that will stimulate light. So here's the active region, which is right over here. And here is where you have electrons and holes meeting and creating and emitting photons. And in a laser, you have two mirrors on the side, or facets, and it creates kind of a resonating area where it can re-stimulate light using the light it's already created, which creates it emits more light. So the way we've grown our lasers is through molecular beam epitaxy. This is a very complex diagram, but you have these different cells, and they each contain a different material, or like a pure element. So you have your substrate right here, and when you open these valves, this is a giant vacuum chamber. So when you open the valves, the materials are deposited onto your film, and you can grow very thin crystalline layers on top of your substrate. And this is just the viewing port, so you can see what's going on in there, and this is the prep chamber. So the reason we're using quantum dots in these lasers is because the industry standard is quantum wells, and that creates the planar region as an active region. And the problem with this is when you have dislocations, it affects the whole planar region, and it creates for a very inefficient device when you do have these dislocations. Quantum dots, however, have 3D confinement, so you'll have like this little square, but you'll have hundreds and hundreds of thousands of them. So when you have a dislocation come up, it's not gonna affect and like pierce through a whole plane. It's gonna pierce through one of them. So let's say you have 100 of them, one is pierced by a dislocation, and the rest of the 99 still work. So these over here are demonstrations of layers of quantum dots that are grown. And here is, so this would be again a base layer. These are the dislocations coming up, and each layer is trapping the layers of dislocations. So as you see, you go through, and you have fewer dislocations as you go up through the material. So I characterize these lasers using both a modular integrating sphere and an optical spectrum analyzer. Ian also used the modular integrating sphere, so it's a little bit of a recap. But we use the Keithley as a electrical current into the laser, and then with the optical output, we measured it using the integrating sphere and obtained the LIV curve, which is where you can obtain the threshold. So the threshold right here the laser's acting similar to an LED, where there is light being emitted, but it's not using the resonating structure. So right at the threshold is where you can see it changing into a laser and creating that resonating structure and actually lasing. So right here, we're looking to minimize the threshold so that you can use these in data centers and use them at lower power, so it consumes less power. And over here, using the optical spectrum analyzer, we're doing power versus wavelength. So again, power like this, but each of these is a wavelength that's being emitted from the laser. These are below threshold, and this is above threshold. You can see there's a peak right where it is resonating. And so looking at these, we can extract the gain parameters and see the injection efficiency of a laser. So these are device thresholds, a gallium arsenide template versus a quantum dot, or not quantum dot, I apologize, gallium phosphide silicon template. So you can see they have very similar thresholds, so that means that the silicon gallium phosphide is within range of the gallium arsenide, which would be, since they have the same structure on top of them, it's kind of the ideal situation because it doesn't have that lattice mismatch. And then also here we have the injection efficiency, which is how many electrons are coming in and how much light is coming out. So again, they both have an average efficiency of around 0.7 or 70%, which again, that means that the gallium phosphide silicon is within range of the gallium arsenide. So again, in summary, the gap silicon devices are comparable to the gallium arsenide, which means they're cheaper, they can be grown on much larger wafers, and they're a lot more commercially viable, which makes it a lot better for data centers because they're not as expensive to implement, and you can grow more, and it's easier to fabricate them, sort of. So next steps in this process is varying the cladding layers, which I mentioned transport the electrons and the holes to the system. And so when you're growing this top layer on top of the quantum dots, the aluminum layers, so these layers right here, have to be grown at very high temperatures, which makes these quantum dots tend to interdiffuse, and you don't get that perfect 3D confinement that you want, which makes them a little bit less efficient. So if we can vary these without varying the electrical loss and thermal properties, that would be the optimal situation. And so I'd like to thank my mentor, Justin, as well as John Bowers for mentoring me this summer, as well as Daewon, Ian, and Bonky, who was in here, for working with me, and then Wendy and Jens, of course. Thank you guys.